Okay, hi everyone. Like Mark, I don't really do too much with adaptation, but I am interested in it. I am interested in precipitation extremes in a changing climate, and to kind of, I guess, motivate people who are interested or do actively work in adaptation. I'll have a little bit of an introduction here. So the major feature that I research is these things called atmospheric rivers, and so this is an atmospheric river hitting the coastline of California right here, and this is visualized using a gridded reanalysis product, and what you see is the magnitude of moisture flux. So it's the magnitude of the movement of moisture in the atmosphere. And these are globally occurring features, but the thing is the amount of observations that we have along the coast of California is unprecedented. So this is a really good test bed for other regions. And so to motivate, interest in adaptation, their impacts in California are quite extreme. So this is the same event that I showed on the previous slide. This is accumulated precipitation, and along the Cascades, this actually ended up with, I think, 6 inches of accumulated precipitation over a roughly 2.5 day period. But they kind of play a dual role. So they're essential to water resources, but they're also a natural hazard that we need to prepare for. And so to motivate that, so this figure at the top shows the change in snowpack, which is very important for water resources, between a very active atmospheric river season in 2016 compared to a not so active season in 2017. And so the difference in these two seasons was a relatively small number of storms not making landfall. And this is a picture of the devastating impacts that they can have when they do make landfall. So this is from earlier this year. And so the overarching questions in my research are, first, how do large-scale circulation features modulate the regional mean and extreme precipitation events related in particular to atmospheric rivers, and how will they change with climate change? I also am very interested about what processes lead to spatial and temporal organization of these features. And then finally, can we better predict precipitation variability and changes through understanding their modulating processes? And I didn't follow the instructions very well, so I don't have a method slide. But the approaches I use range from employing simple conceptual models of the processes to using, in current research, I'm using the community Earth system model to look at mesoscale convective systems over the central United States. But my process usually begins with just analysis of gridded climate data, trying to understand the processes, and then testing hypotheses from there. And so some examples of past research. So here, this is a comparison of persistent, spatial and temporally persistent atmospheric rivers off the coast of California, and trying to understand how these features are different and what sort of large-scale circulation sets up for these features. And the second figure here is from a project where we looked at a comparison of end-of-the-century climate change projections to the historical period, and compared the interannual variability. So this is a comparison of 1980 to 2080, all the way up to 1999 to 2099, looking at the interannual variability and behavior of these atmospheric rivers in historical compared to the future climate. And one of the big key take-home points from this paper was an increase in the number of atmospheric river days in the future climate, though not so many changes in I guess, interannual variability. And so I don't have too much. I'm not going to keep everyone from their socializing. But as far as what I teach, so this is actually my first semester teaching, so I am teaching Earth system analysis. So it's a broad overview of the mathematical foundations for data analysis, and there's a really nice lab component too, so learning MATLAB and Python and tools for that. So with that, thank you.